Hello and welcome to my 11th lecture on operating system development. Today I'm going to be talking about a relatively important concept, and that concept is memory allocation or memory management. So previously I talked about input and output devices and general peripheral communication, and that means that I already succeeded in explaining one of the things that I wanted to talk about in this series, and now we're going to go a bit faster because a lot of the series was just a general foundation, such as, how a bootloader works, or the GDT, the IDT interrupts, and all that hardware stuff, and now we're getting into some actual operating system theory, which is not, and this is the point at which you're not longer making a piece of software that works directly on hardware, like bare metal software. You're starting to implement algorithms for actual management of processes. And today I'm going to be talking about the general ways that memory can be handled and the ways that memory can be allocated, and about the general primitives that an operating system should offer in order to manage memory. So any operating system, or at least any good operating system, well, this might not necessarily be true. I guess there are a lot of ways you could theoretically implement this, but most operating systems have some sort of equivalent, or literally those instructions, which are some sort of malloc, which just stands for memory allocate, and some sort of freeing instruction. So the primitives that an operating system should implement in order to allow a given process to use the operating system as a memory management is some sort of memory allocating primitive and some sort of freeing primitive. The first one is a request. It's requesting to the operating system that it wants to receive a chunk of memory of a given size. Freeing is the sort of opposite primitive, where you're saying that, where a given process is saying that it no longer needs a given chunk of memory, and it gives it back to the operating system so that this chunk of memory can be allocated to some different process. In reality, since you're going to be using paging, which I've already talked about, and I've talked about how physical and virtual memory works in my paging video. You're going to be allocating pages to different processes, and you're going to use different, for example, page flags and things in the page table in order to keep track of, for example, which pages can be used by which process. And even if a given process is going to be allocating less than your page size, the process is probably going to be given a page anyway. Right, and not only that, but this is also, so obviously you will implement errors and such for pages, and that's one way that processes will be able to discern what memory is allocated, and the operating system will be able to know whether a given memory operation is legal or not. But also the use of segmentation, right? So I've talked about segmentation before, which is another virtual memory management technique. And here a segmentation can be useful. Yet again, the ideas of segmentation in order to give different segments of memory to different processes. And this gives another way to handle such errors, because when a process tries to write or read from a memory address that it is not assigned, you might know this from just general programming as a segmentation fault or a segmentation violation, and that's because you're writing to outside of a segment that was dedicated to that. Right, so you'll need some way to actually enforce this, just like that, which is going to be done for paging and such, and you actually have to implement those two primitives, which are malloc and free, which are actually going to decide whether you can allocate a given chunk of memory and are going to check whether something is free or whether just free is. So a malloc is going to take some sort of size, that size usually being in bytes, and it's going to request a bunch of memory of this size from the operating system. And what malloc is going to return is it's going to return the base memory address of the allocated part of memory. So, for example, if I had, the random access memory, and if I had the RAM, and the operating system would know that somewhere at this point, obviously in practice this would be virtual memory, right? And it finds some values here that are free, and what it does is it knows that this is now, that this belongs to a given process, this is allocated to a given process, and it gives back the base address of where it has found those 3 bytes. Okay, so, right. Memory allocation, the memory allocation primitive malloc, right? It takes an amount that you want to allocate, and it gives you back the address at where this allocated memory is. A virtual address in practice, right? So it gives you back this virtual address. And then the free primitive is a primitive that takes a given memory address, a base memory address of something that has been, for example, previously malloced, and now it will say, okay, this sort of chunk of memory that was allocated at this memory address doesn't have to belong to me anymore. I don't need it as a process anymore, and this is freed up again, and it could be allocated by another process. So this doesn't return anything, it just takes a memory address at which memory is supposed to be freed. All right, so that's the general abstract idea of malloc and free. And now let's look at some actual algorithms as for how you could implement those two primitives. So, the first algorithm that I'm going to be talking about is something called a bitmap allocator. And a bitmap allocator is very inefficient, and I generally wouldn't recommend it, but I'm going to talk about it for historical reasons, and also just to generally give probably the simplest solution to see why it is so horrible and how we can improve upon it. So the idea of a bitmap allocator is you have your memory, and it is split into, well, for example, pages. And each page is obviously going to be allocated or not. It's going to belong to a given process or not. And the idea is you simply have a bit array, we have some sort of bit array where for example, all of those bits are going to be 0 by default, and you want to consider whether a given page is free or not. Or, well, if you're not working with pages, or if you're working with whatever else, if you want to make those bytes or whatever. But generally, you have split your memory into those memory regions, and you have a bit array where each bit corresponds to each region of memory. And 0 is simply going to mean that it is free, and then 1 is going to mean that it's allocated, that it's not free. And that makes the implementation of a malloc in free extremely easy, and also for checking whether a given thing is allocated or not. So a malloc would be simple. It would be a brute force search through the array, and it would try searching for a 0. Once it finds a 0, it changes that to 1. It sees we need some data structure, we need some mapping. As for, or you could probably just have a linear formula that maps it. You would have a mapping. Hey, this is the page that this corresponded to. So right now this is going to be allocated. And yeah, so that's basically how you allocate something. And then if you want to free a given region of memory, then what you would do is you would take a look at which bit corresponds to it, and then you would simply change it to a 0, and that would free that chunk of memory. So that's the general idea of a bitmap allocator, because you have a bunch of bits which are mapped to pages or bytes or whatever, and they keep track of whether they are allocated or not. Right, so let's actually analyze how good of a solution this is. For any byte that you want to allocate, you're going to have to do a full brute force search of the entire array, which has linear complexity. Because, you know, in the worst case, if you have all ones and then a 0 at the end, what this would mean is that you would have to search through the whole thing in order to find a 0 somewhere at the end. So allocating is pretty expensive, right? It's a linear task for every single byte, but then if you want to allocate n bytes, because you usually want to allocate a given amount of bytes, this actually becomes a quadratic complexity problem, because you have to do this linear procedure a given amount of times, you know, dictated by how many bytes you want to allocate. So this ends up being like O of nk, right? Which is basically like a quadratic complexity. And an oversimplification of sorts. But it just goes to show that this is actually a very bad solution. And then if you want to free something that is relatively efficient, because it is actually constant time, because, well, freeing would just be, you know, changing a given bit to 0 where it was previously 1. So freeing is actually very efficient. It is constant time. But yeah, that's the idea of a bitmap allocator. So a possible improvement upon this is a method that is relatively efficient, and it's pretty easy to implement. It doesn't require anything that would be necessarily complicated, and that is something called the Freelist. The Freelist algorithm. So the idea is you have your memory. And we have a split. And the idea is that you use a structure called a linked list, right? So you construct a linked list. Where each memory region points to the next one. Yeah, and you would have some sort of null to inform you that the linked list is finished. Right, so you keep track of 2 pointers, and one of those pointers is going to be the head, and you're going to keep track of the tail. And I should have written down in the previous one that it was a bitmap allocator, but this is something called a Freelist. So you have a head and tail, and in order to allocate a byte, what you would do is you would take a look at the head, and this Freelist, this whole linked list, it simply is a linked list of all different bytes that are free, right? Or in practice, it's going to be pages that are free. So you keep track of all the free chunks of memory, and so since it only contains free elements by definition, well, everything is free by default, right? And also by definition, since the free list only contains bytes that are free, you can simply grab the address, which is over at the head. And when you grab this address over at the head, that's the result you return as your malloc. And then you simply set the head to the next node of the linked list. And therefore, the allocated byte is no longer a part of your free list. And this means that you'll never set the head to it, and therefore the malloc will never try to again allocate this allocated region. Yeah, and you could do this, and you could always just return the address of the head, and that's your malloc. And since you always have access to your head, you can actually see that mallocing using the free list for a single byte is actually constant time, which is pretty good. It's very good in comparison to the linear complexity of the malloc offered by the bitmap allocator. Obviously, as some sort of cost of the free list is that you have to initialize this linked list. But in any algorithm in an operating system, you don't care that much about the efficiency of initialization, because an operating system is a software that is supposed to boot up for a non-trivial amount of time anyway. So executing a couple instructions here and there to initialize a given technique is not that important. Obviously, it still is important, which is why I'm not saying that the Freelist is the best thing to ever exist. I'm just saying that you usually don't have to worry about it that much in practice. Okay, so you have the tail, and the tail is useful for freeing, because whenever you want to free a byte, what you would simply do is, instead of making the tail point at null, you make the tail, the previous tail, point to the block that you have now freed, which becomes your new tail, that now points to some null. And that way you're going to have it freed. And again, since you store the position of the tail at all points, at all moments, freeing is going to be constant time. So freeing and allocating a single byte are both constant time, so that's pretty cool. But obviously, if you want to actually allocate something bigger, you want to allocate n bytes, obviously you're going to have to perform this constant operation n times. So allocating, a multitude of bytes or a multitude of pages is still going to have linear complexity. And this is sort of a problem in a sense, because oftentimes in an operating system, a process will try to allocate a very non-trivial amounts of memory, Like, for example, when it needs to store a file in the RAM, or like an image or a video file, right? So it's going to want to allocate more of that virtual memory. And because of that, people have tried to improve upon existing algorithms and create algorithms that are sort of designed to sort of fit things of, a slightly bigger size. So, this was Freelist, pretty good algorithm. But now the next algorithm that I'm going to talk about, that was supposed to be designed for now also being able to handle larger sort of units of allocation. And that is something called, and I have a relatively hard time pronouncing the word, a buddy allocator. That's not centered at all. I'll take that. So a buddy allocator, the idea of a buddy allocator is that you have your virtual memory, which is some sort of power of 2, which that's the usual reasons why you can see around 6 and such being designed so that it is a power of 2, because that makes a lot of allocating algorithms a lot easier, and you don't have to fill it in with zeros or whatever and do some extra quirks. But anyway, you have this memory which is some power of 2, and whenever you get some sort of request like, oh, I want to allocate 3 megabytes or whatever. Right, let's say we want to allocate 3 megabytes, and we have 64 megabytes here, or maybe bytes, let's say, if you want to be precise and everything, the powers of 2, whatever. So over here, 3 megabytes. and then a memory with a size of 64 megabytes. So we want to allocate this, and the idea is that we're going to be splitting our entire memory until we can find basically a region that satisfies two properties. The first property is that this is still going to fit, right? And the second property is that if we split it once more, it wouldn't fit. So we find the minimum sort of block such that this is going to be contained in it. So let me provide an example. We're trying to allocate 3 megabytes, and we have a memory of the size of 64 megabytes. And what we do is we check, well, would this fit in this memory? Well, of course it would. And if we split it in half, would it still fit? Well, yeah, so let's split it in half. So now we're going to have 32 megabytes. And, well, would it fit in 32 megabytes? Well, it would, but it would also fit in 16 megabytes. And then, would it fit in 16 megabytes? Well, it would, but it would also fit in 8. And it would also fit in 4. But notice that once we get to 4, right, so we have this whole thing, which is 16, and then we split it in half, so we have 8, and it would fit in 8, then it would fit in 4. But notice that it would fit in 4, but it wouldn't fit in 2. So we found the middle block, and thus we allocate it. Right, so that is the idea of a body allocator, and you can see how for larger amounts this would be way more efficient. So we're splitting a power of 2 constantly, so this sort of search actually has logarithmic complexity, base 2, of course. And in fact, yeah, whenever you're allocating those bigger amounts, this turns out to be a relatively efficient method. Obviously, if you want to allocate a single byte, it would perform a search for that byte, so a body allocator would be worse here than, for example, something like the Freelist. But it would be better than something like the Bitmap allocator. Yeah, so obviously there are general improvements upon this and things you could do. But there are also, a lot of fundamental things that are wrong with the body allocator. And for example, one of those things, and you might have already noticed this, is a sort of internal fragmentation, which is a big consequence of this sort of body allocator. Because if you've sort of kept track of what we're doing, right, we were trying to allocate 3 megabytes, but hold on, what we've ended up actually doing in reality is allocating 4 megabytes. And this is because, well, in the body allocator, if we tried to allocate something again, we would try to find this region, but obviously a free region. We can't split anymore if the regions are allocated, right? So you obviously have to take that into consideration to your algorithm, that some blocks are going to be already allocated. And this is actually some horrible wasting of space, because we have tagged an entire 4 megabyte block as allocated, Whereas there's a whole 1 megabyte that the process is not going to use, because it's still going to be flagged as a segmentation violation. It shouldn't, have sort of access to the memory that it is not allocated, but it's not like any process is going to allocate it anyway. So this leads to horrible internal fragmentation, where you're going to have like 3 allocated, megabytes, and you're going to have 1 megabyte, which is free, and maybe even if something gets placed there, it has to be under 1 megabyte, and right, you can't have contiguous blocks that would have a higher size, because, well, then something might allocate this, and over here you only have 1 megabyte, so it leads to this internal fragmentation. Where you can only allocate here if you had 1 megabyte, whereas this could be more useful somewhere in order to allow for higher allocation sizes. Okay, so we can see that the body allocator is indeed fundamentally flawed in some ways. Right, and freeing, I think freeing is relatively obvious. I mean, you just take a block and you mark it as not allocated anymore. So that the algorithm of splitting stuff can take the unallocated block into account again, right? And be able to allocate it. Right, so obviously a good algorithm for, larger sizes, and there are some optimizations and, switching of algorithms and stuff that would make this general solution also relatively good for allocating just singular bytes. But yeah, generally a very good design to think about the fact that often you're going to allocate bigger, blocks of memory. So that's a body allocator. And nowadays there are a lot of algorithms which, in those sort of operating systems that try to consider themselves theoretically elegant. So for example, the Unix BSD systems, they try to make a solution which is even more theoretically elegant and allows for a lot of efficiency, and fixes some of the problems we had with our previous allocators, and that is something, well, it's not anything innovative. Well, perhaps this precise use case is pretty cool, but in general, this is a structure that's used all, everywhere in computer science, all around the place. And that is to just use some sort of balanced search tree. So we use some sort of balanced search tree. This can be something like an AVL tree and stuff, but I think the one that is most commonly used in operating systems is something called a red-black tree. So a red-black tree is, something that is a red-black tree is a sort of it's a balanced search tree that I'm not going to talk about all the different operations in it on this video, because there are a lot of resources for how to insert and remove things from red-black trees, because for this sort of series I assumed that the viewer is a competent programmer, and any competent programmer should be familiar with balanced search trees. I think that is something to expect from any competent programmer. So the fundamental ideas of a red-black tree, which should be the sort of recap, is you have nodes. It would be cool if I would have a red marker. I used to have them, I don't anymore. They would be perfect for things like red-black trees. I wonder where the name red-black tree comes from. Maybe because professors actually just had red and black markers and it was easy to draw. I don't know. Either way, each node in a red-black tree has to either be obviously black or red. And here I explicitly have drawn something called nil nodes. So these are just going to be your termination nodes. These are going to be literal nulls. So you don't actually have to care about them. I just have, explicitly drawn them. But the sort of algorithmic aspect of them, and the one that you consider in theory, is that you consider those nil nodes to be black. And you have black and red nodes if you're a red-black tree. And the sort of next postulate is that a red node cannot have a red child. And then the final one, which is actually sort of responsible for the very reason that the red-black tree is balanced, and all the operations of a red-black tree consider this postulate. And if a given operation still, keeps this postulate intact, then, this is a balanced operation. And this key thing, this key rule of a red-black tree, which allows for its balancing, is that the path from any node to any of its nil descendants has to go through the same amount of black nodes. And one can easily see how that would make the tree balanced together with the previous postulate that a red node cannot have a red child. Because if it could, you could just spam red childs, basically. Red children, childs. Oh my god. You have this thing where in English, obviously when you have a word in a normal context, you would say the word in plural in a normal way, but when it appears in a very specific scientific context, you suddenly forget that the word means what it means. Oh my god. Childs. Very cool word, man. Children. You could basically spam red children, and when you take for root, obviously it would only go for red children, so it would go through the same amount of black children. So the amount of black children which it goes through, the black child count, has to be the same when you're taking any path to any of its nil descendants. So any path that it takes to the end has to go for the same black nodes, yeah. That's the idea. But yeah, so that's a red-black tree. So that's just an arbitrary choice of a balanced search tree. And the idea is sort of the same as with the body allocator, that, okay, we can search for something in logarithmic time, and we can search for something that is a larger amount of bytes or pages in just one logarithmic complexity search. And that is true, and the body allocator had those different problems with internal fragmentation and stuff. But the red-black tree approach, or just the balanced search tree approach, is designed in such a way that many of the flaws, like for example the fact that it would be more difficult to get to, tiny allocation amounts that could be common, is that you can place, because basically the nodes are going to contain two things. They're going to contain the address at which you have unallocated sort of memory of a given size, and then obviously the second parameter is going to be the size. What you're going to be actually searching for is simply the size. You're going to, because obviously the process, the only thing it cares, it doesn't care about the memory address that it receives. It just cares that it has, a free memory block of a given size of that address. So you search for a given size, right? So, for example, let's say I want to allocate 2 bytes. So I, do this red-black tree search, logarithmic complexity. And I'll get the number 2. And I think there have to be some additional rules for the contents of the nodes for the search to be logarithmic. I can't remember. I studied red-black tree a long time ago. Either way, it doesn't matter. The key idea is that you can find an allocation size. Well, obviously, you could have a red-black search tree where you would have, for example, 50 here, so you have like greater amounts to the right and so on to the left. I mean, that's one way you could easily make it logarithmic. So I guess that would work. So now it's a red-black search tree, not just a red-black tree. Either way, you end up with a sort of logarithmic search, and you find a size that satisfies you, and great, you simply return the address of that node and you delete the node from the red-black tree. And that's how memory allocating works. And since it's removed, it's not going to be allocated again. Amazing, and this solves a lot of our problems that the body allocator has while keeping the general complexity, time complexity and efficiency of the body allocator. So what is the problem with using a balanced search tree for memory allocation? Well, the problem is that this task of creating the tree, constructing the tree, and picking right sizes and updating it in real time. And whenever you free freeing is easy. I mean, just adding the nodes to a red-black search tree. But the idea of constructing this tree, which would have appropriate values and such, is a trivial task, is a non-trivial task in and of itself that has a lot of research applied on it, and you have, other algorithms for that. I'm sure you can come up with some ideas of how this could be done, but it's also just good to take a look at the code of projects such as, Unix BSD systems, because I'm pretty sure most of them use red-black search trees for things like that. Right, so, I mean, obviously it has to follow some extra postulate to have logarithmic search time, like the greater values to the right and so on to the left or whatever. So that it is an actual search tree. And then the red-black thing is just balancing. Okay. So that's pretty much everything I wanted to talk about in this video. So I talked a bit about, memory as this resource that processes request and they later have to free it so that a different process could allocate it. You're going to use different things such as the paging and segmentation in order to, have some way for the operating system to enforce those things for individual processes. And that's the general idea of memory allocation. So thank you a lot for watching this video, and I hope that we get to see each other in the next one about file systems, where we will come back to the topic of search trees.